Okay, welcome to another BIMSA member seminar. It is a pleasure to have Professor Pavel Nikitin. He's an associate professor in BIMSA in the representation theory group, and he's going to talk about asymptotic representation theory.
Thanks a lot. It's a great pleasure to have a talk here at BIMSA member seminar. I want to speak about the asymptotic representation theory. That audience is quite broad here. Let me briefly recall what representation theory is about. So I take a group and the vector space V, and I consider the homomorphisms from my group to this to the corresponding general linear group. In a sense, this is a general way to study symmetries of the underlying space. And I restrict myself to a simple case. My G is finite or some classical matrix group, and my V is finite dimensional complex linear space. If I want to study such objects, it's natural to decompose it into some minimal blocks. So I decompose my V into the direct sum of the invariant subspaces. When I restrict myself to a particular invariant subspace, I get a sub-representation. I combine together all the equivalent ones, and I get a decomposition of my representation into the sums of irreducibles with some multiplixities. And the basic questions of the representation theory are, given a particular group, how do we describe the equivalent classes of the irreducible representations? And known that, how can we describe the multiplicities, either in general, usually via the character theory, or for some particular classes of reducible representations we're interested in applications. I want to speak about the asymptotic representation theory. So instead of one particular group, I pick up an increasing chain of groups. And now I ask similar asymptotic questions. So first of all, I can ask what happens to a particular irreducible components when n tends to infinity. And I will not touch these questions at all. I will focus on the second one, the asymptotic behavior of the multiplicities. Today, I will restrict myself to the chain of general linear groups. Let me recall that if we want to parameterize the irreducible finite dimensional polynomial representations, it is done via Young diagrams. Here is a Young diagram for you. We have rows of identical boxes, and the number of boxes is non-increasing. For the general linear group GLN, the only restriction is that my Young diagram has at most n rows. And I will also speak about the irreducible representations of the symmetric group. For the symmetric group SK, my reducible representations, once again, are parameterized by the Young diagrams with the only restriction that number of boxes is K. Now I know the parameterization of irreducibles. Let me introduce you the first reducible representation I'm interested in. I take the kth tensor power of Cn. I decompose it into the irreducibles, and I want to understand the asymptotics of this decomposition. Let me recall that we have so-called Schur-Weil duality. Namely, I can have a second action on this tensor power, namely symmetric group acts on my tensor space, just permuting all the components. And if I consider both actions, then the decomposition of my tensor space is the direct sum of the tensor products of the irreducible representations corresponding to the symmetric group and to the general linear. Now, if I forget about the action of the symmetric group, we see that the multiplicities here are given by the dimensions of the corresponding irreducible representations of the symmetric group. Now I can ask the questions, for example, how a typical component of this decomposition behaves. If I speak about some typical components, I should have some probability measure. So let me introduce a measure like this. For each irreducible component, the most natural weight is something proportional to the dimension of the corresponding irreducible representation. In other words, let us pick up this decomposition, take the dimensions of the left-hand side and of the right-hand side. We see that we have n to the power k here. We have the sum of the products of the dimensions here. We normalize both sides by n to the k, and we get this measure. My parameterization here is by Young diagrams. So if I have a reasonable measure here, I can forget about the representation theory and ask, I have a random Young diagram with respect to this measure. What is the corresponding asymptotics? How can I describe the asymptotics of a random Young diagram? It turns out that for very general class of measures, there is so-called limit shape. Given my measure, I can present you a deterministic curve like this. And when my parameters are big enough, it's highly improbable that my random diagram is not close enough to my limit shape. In fact, the probability of all such diagrams is exponentially small when n tends to infinity. Known the limit shape, the next general asymptotic question when I think about the limit shape in general is, let me now subtract my limit shape from the random diagram. Then you see that I have some fluctuations around 0. And well, how can I describe these fluctuations? These are one types of questions. Another type of question is to speak about the local asymptotics. Bulk asymptotics. We see that non-trivial behavior for my diagram is somewhere between 0 and 4. If I pick up a point strictly inside 0 and 4, somewhere here, for example, and I now take a small neighborhood, and I'm trying to have a precise understanding of the limiting behavior of my random diagram in this neighborhood. It turns out that the resulting behavior is universal, and up to some scaling, it does not depend on a particular point. This is my bulk asymptotics. I can also pick up an edge here or here. I can try to understand the local behavior around an edge. And I also have an universal answer for generic set of parameters. And this is my edge asymptotics.
Can you explain what the picture is exactly?
This picture?
Yes.
Sorry. I have a random diagram. Here is my measure. Now I can pick up my diagram at random.
At random in this decomposition depends on problem.
At random with respect to this measure. And like with exponentially small probability, my diagram will not look like this.
So the diagram is drawn now
Yes, I will explain why it helps. Yes, I rotate my diagram to so-called Russian coordinates, which helps to deal with local asymptotics.
What's this value 4?
Why it helps to draw it like this? We will see it in.
Number 4.
On the x-axis, you said something like 4.
You see that here is our curve. It's non-trivial here, and starting from here, there is like everything freezes. There is nothing interesting.
Can you write a description of the measure just in terms of lambda?
There is a better way to do it. We'll see it in a couple of slides. And so, okay, we have universal asymptotics for the bulk, for the edge, and they are well known. I will show them at the end of today's talk.
The line is really the boundary of the Young diagram, kind of?
Yes, the boundary of my Young diagram in some very strong sense tends to this particular line, precisely.
Asymptotics of the
Yes. So, and for me, one of the main reasons to deal with the particular family of measure I will present you in a minute is this critical asymptotics. It happens that in some cases, the resulting measures are not like, say, this. We have some nice degenerations, and it seems that people doesn't know much about them. To present my family of measures, first of all, let me say some words about skew Howe duality. I pick up the tensor product Cn tensor Ck. I consider the exterior algebra. It turns out that I have similar duality. I can decompose it as a tensor product of irreducibles. And here the sum is over all the diagrams that fit inside the rectangle and of size n times k. And the correspondence between this irreducible component and this is as follows. I pick up a diagram, I transpose it, and I take the complement inside my rectangle. The first thing we can do, once again, we can pass to the dimensions, normalize everything, and we get a measure like this. Now I will explain why it's convenient to rotate the diagram. I want to introduce another language. Now I have the border of my diagram. It consists of downward and upward segments. I mark the midpoints of the downward segments. I project them onto the horizontal axis. And now, instead of a random Young diagram, I can speak in terms of random point configurations, sitting in half integers. And, well, for this particular measure, it turns out that I have a nice formula. Up to some normalization, I have the square of the van der Monde determinant times the product of the weights of this form. Such random configurations or random point processes are so-called polynomial ensembles. This particular weight corresponds to the Kravchuk polynomials. We get Kravchuk polynomial ensemble. I want to have an argument for some universality. So instead of one measure, I want to give you a family of measures. So let me now take characters of left-hand side and right-hand side. We know that the characters of the irreducible representations for GLN are Schur polynomials. And I will recall some nice geometric definition of these quantities in a couple of slides. So I have a measure of this form, and I want to understand its asymptotics. First of all, as usual, we do have the limit shapes. And I don't want to write you a precise formula here. For
this lambda bar there.
This one. Let me come back for a moment.
Yes.
Can
I remember.
The point that doesn't want because now you have to try these count.
Can you help me? Can anyone help me? Backspace. Okay. Thank you. No, the other way around. This was,
Yes.
so this one transpose and take the complement. So we do have the limit shapes for general sets of parameters. For the fluctuations, it's trickier. The usual way to deal with the fluctuations is I pick up some test function. I sum up my test functions over my random configuration. And I subtract the mean. The mean is the integral with respect to the limit shape. So this part represents the random configuration. This part represents the limit shape. I see that the difference is governed by the Gaussian distribution. The only thing I want to stress here is that we do not have the proof for general case. We have the proof only if the associated polynomials are good enough. if we know the asymptotics for the associated polynomials, let me come back for a moment here. If you remember this here, the associated polynomials are, say, the Kraft-Chuk ensemble. So if we know the asymptotics of the corresponding polynomials, we do have this type of central limit theorem. In general, unfortunately, we don't. Let us move on towards the local asymptotics. To do the local asymptotics, I want to understand better my Schur polynomials. Let me
you already know. You don't have some nice formula.
If I have like nice parameterization, I have reasonably nice but still cumbersome formulas for the limit shape. For some general parameterization, we know the existence, but there are no exact formulas. So my dimension of an irreducible representation. I pick up my diagram lambda. I consider the corresponding point configuration. For my GLN, I draw n vertical lines. I put my point configuration here. I put a trivial configuration here. And I try to write all the non-intersecting paths from here to here. When I count them, I get the corresponding dimension. Now, if I want to understand the value of my Schur polynomial for particular values x1, x2, so on, now to each path of this type, I assign a weight, some monomial in x1, x2, so on, and I add up all such monomials. In particular, we see that if my x's and y's are non-negative, I do get a probability measure on the previous slide. And a key point here is that if I have some weighted sum of non-intersecting paths, there is a nice combinatorial lemma, Lindstrom-Gessel-Vienot lemma, that tells me that if I have this weighted non-intersecting paths, then my combinatorics is governed by some nice determinantal structure. Why it is helpful to me? I want to understand my random point process. I want to define my random configurations. One of the convenient ways to do it for me is to do it via so-called correlation functions. I fix a finite set. On this picture, my finite set is I1 and I2, just 2 points. Now I take random configurations X, and I write the value for the probability that my fixed configuration sits inside my fixed, say, set sits inside my random configuration. An important point is that if I know the correlation functions, that I know the process. This is, in this case, this like simple inclusion-exclusion process. It turns out that all the measures we're discussing are so-called determinantal. That is, my correlation functions are given by some determinants of a particular correlation kernel, a particular function of 2 variables. I want to understand limiting behavior in the neighbor of a particular point. So I want to understand the limit of the point processes. It turns out, and it's easy to believe it, that if all my expressions are determinants of some correlation kernels, it's sufficient to understand the limits of the corresponding correlation kernels. If I know the limits of the correlation kernels, then I know the corresponding limiting correlation kernel. Therefore, I know the corresponding limiting point process.
This A is X is the set of A's, right? A1 to AK.
Yes, X is my random configuration. This is my A1, A2, and so on.
I1 and I2 are not in X. Right?
Yes, yes, it's easier to draw a picture when, yes, all these I's are not. But in general, of course, sum of A's can be sum of I's. Nice. So because of this non-intersecting path structure, I have corresponding determinantal structure. I have my determinantal kernel. Therefore, it's sufficient to understand the asymptotics of my kernel. And I don't want to write you the formula for the kernel itself. But I want to tell you a couple of words about the asymptotics. So in the bulk, we have some interval where we have non-trivial behavior. I pick up a point. It turns out that the limiting behavior is described by the so-called discrete sign kernel. Here it is. When I am sitting for generic parameters at the edge, then my edge asymptotics is given by so-called airy kernel. And for example, if I try to understand the behavior of the, say, rightmost particle, my airy, we do have for the edge the rightmost particle. It's governed by so-called Tracy-Widom distribution that appeared several times in the previous talks. For example, Konstantin Khanin was discussing this Tracy-Widom distribution as well. And AI is just airy function. I had no place to write it here. Probably we don't need it. What I'm more interested in is so-called critical asymptotics. Here we have better known situation, the critical situation when I have two intervals, and when n tends to infinity, they touch each other. This is also a well-known case. It is governed by so-called Pearcey kernel. I have Pearcey asymptotics, cusp asymptotics. What I want to show you is less known situation when I have an asymptotics near the corner, and it is governed by so-called discrete Hermite kernel. First of all, what do I mean by the asymptotics near the corner? Here is a picture for you. So my limit shape should end up in a corner. My C is a ratio of the sides, and it's easy to understand that when everything else is fixed, I have precisely one C such that my limit shape ends in a corner. So I pick up this type of C, then my K is Cn plus something. I can have an additional term of lower order. So it's Cn plus some S times the square root of n plus some lower terms. And it turns out that if I have this behavior of K, I have some nice degeneration of the airy. I actually don't have the corresponding airy behavior in the limits, and the limiting behavior is governed by the discrete Hermite kernel. Initially, it was defined by Borodin and Olshansky in 2007 when they discussed the Schur-Weil measure that I've defined in the very beginning. And one of the reasons for our current paper on skew Howe duality was to convince ourselves and others that we do have a universality and universal behavior here as well. So this is our recent work with Dan Bittet, Anton Nazarov, and Travis Scrimshaw, when we were able to check in particular that if we have this corner asymptotics, then the corresponding limiting behavior is of this form, is given by the discrete Hermite kernel. So if you want to recall like one thing from the talk, I highly recommend you that you remember that there is this less known universal asymptotics. Now, as I probably have, say, 5 more minutes, let me briefly tell you what are the connections with other fields and what are the future topics of research. First of all, as you can see from my definition of the dimensions and of the Schur polynomials, actually we're speaking about the 3-dimensional random structures of this form. So I have some non-standard gluing here. It's not difficult to explain if our triangles here face either right or left, and we have all the possibilities. We have a nice measure sitting on each of these diagrams, and actually what we're speaking about, we restrict ourselves to the main section of this form. So our work is in progress is we want to understand the limiting behavior of these three-dimensional pictures. Once again, we have some universal behavior when we're far from this main section, but we hope that we'll have something less trivial, more interesting on this section. Sorry, not yet. Now, if you come back to this picture with non-intersecting paths, and you know the 5-vertex, 6-vertex models, you probably can see that if we write our pictures, if we draw our pictures in slightly different way, what we actually get is a version of this 5-vertex, 6-vertex model, and therefore there is like a direct connection to the integrable models here. And also, now we speak about GL and GLK, we can generalize it. We can generalize, first of all, to the other types of Lie algebras. And we do not have all the same list of the results, but we do have some partial results here. It seems that very similar argument should work also for super algebras. And all these parts are semi-simple. Another more tricky way is to speak about the quantum groups. And Nikolai Reshetikhin talked about the case of the roots of unity several months ago, when the situation is not semi-simple, but then now it's more or less clear what happens only for UQ of SL2. And it's really nice to understand what happens, at least for, say, SL3. And one more thing I'm really interested in. This one, people who are doing random matrices, they know that we do see this area and sign limiting behavior because it's like believed to be universal. We try to find something like this discrete Hermite situation, but we have find nothing. So if some of you has some hints, for me, it would be really nice to understand better the corresponding connection here. And probably that's all I want to say. Let me leave this nice picture here. And thank you for your attention.
Thank you very much. Questions?
Can you explain how to understand this picture? Those triangles?
Can you explain the triangles? What are these pictures?
Yes, if we come back to this picture, what you can see is that I actually have triangles that face right. So if we want to write the product of such two dimensions, it means that I will have some triangles facing right and some triangles facing left. So they correspond to the point configuration that encodes my diagram and to the point configuration that encodes this transposed complementary diagram. And this is the place where we need some additional tricks. So for the usual Schur measure, when we have S lambda, we don't have like this type of complication. And for example, the derivation of the integral representation of the kernel that I have nothing about is more complicated in this iteration.
Can you explain how Kravchuk polynomials connect with other type of polynomials? Schur, McDonald, others.
So your question is, we have Schur polynomials, and we know that we can start from McDonald polynomials, and after some, we have two additional parameters, Q and T, and you want to understand what are the analogs of the Kravchuk polynomials in this case, right?
I try to understand who is Kravchuk polynomial in terms of Schur polynomials of other type of polynomials. Can you understand the like characters of some groups or something like this? Okay, what is definition of Kravchuk polynomials except a Butt measure?
No, the definition is I have a weight. Sorry for that.
So definition is orthogonal polynomial with this measure.
Yes, with this weight.
Any explanation with type of any type, algebra, something.
Well, the connection between the corresponding Schur polynomials and the Kravchuk polynomials is that, well, you have these dimensions, you put like identities everywhere, you get this type of measure, and this is the connection. For example, if you think about the principal specialization, if you take Schur, it was written somewhere here, if you take the geometric progression, you can find so-called Q Kravchuk polynomials. For some other specializations, you can get some other more or less known discrete orthogonal polynomials.
More questions? Okay, let's thank the speaker again.